All right, let's go ahead and get started. I see some of you or hear some of you talking about the homework, so that's a good thing. I like you to get started on that early, so if you have any questions, you can talk to me before I leave town on Saturday. So it's due Tuesday. Again, you have to submit it on Blackboard. It's a little bit more complicated than just turning it in class, but I think that you guys can figure it out. So today we're continuing with our review of last semester. We're on chapters 4 and 5 today, so this is where it starts getting interesting. We start applying some of the things that we've been learning up until now. So we're going to talk about open and closed systems. We're going to review mass and energy balance, and then also look at steady versus unsteady flow. And I will do several examples today that should be helpful to you as you're doing your homework in case you've forgotten how to do these types of problems. You can always look back at your homework from last year too, and your notes if you do forget. So just to review, the energy balance is the net change of energy in the system, and it's equal to whatever's coming into the system minus whatever is leaving the system. So this is in its most general form. We're not concerned with closed or open systems. We're not looking at it in the rate form. This is just the most basic general form of the energy equation, and we'll apply it into several different systems, several different scenarios to see how it changes depending on the application of it. When we're talking about our energy coming in or out of the system, there's a couple of different ways that it can come in or out. With a closed system, it's only via heat and via work. Okay, there is no mass transfer in a closed system. That's the definition of a closed system, is that mass doesn't cross the system boundaries. So if we're looking at energy that's driven, energy change that's driven by a difference in temperature, we call that heat. And anything else pretty much is work. And work crosses the boundary not necessarily in a physical manner. Sometimes boundary work is represented by a boundary moving. But a shaft that crosses the boundary of the system is considered work crossing the boundary, even though the propeller itself is inside the system. Similarly, if there's any kind of an electrical connection to our system, that would be considered work crossing the boundary of the system. In speaking of boundary work, we can look at it as a force times a distance. So if we look at the basic piston-cylinder device, either we're enacting some force upon that piston, or the fluid inside the piston itself is exacting a force upon that cylinder. So we can look at some incremental change in distance, and we can find the incremental change in work due to that slight change in distance. We can rewrite this force as a pressure times an area, because we know that the force on a surface of a flat surface is just equal to the pressure times the surface area. And then we can combine those terms, ADS, into a dV term. So this is the derivation of the equation that we use for boundary work. Used it all last semester, and we will use it quite a bit in this semester as well, particularly as we go on to chapter 8 and we start deriving exergy. So the boundary work is just the integral of PdV. And in the case where the pressure is constant, it can come outside the integral. And if there's some linear relationship to this volume change, then we can just say that it's V2 minus V1. If we don't know that functional relationship for the volume and how it changes with the distance of the piston-cylinder device, it becomes a little more complicated. You have to use numerical methods, or you have to know that relationship. However, in many cases, it is linear, so it's pretty easy to do. So that integral, of course, is the area under the curve on a PV diagram. So if we were to look at this PV diagram at some incremental area within that surface, that would again represent the amount of work that's done as we change this distance in our piston-cylinder device. So we can add up all of these incremental areas to find the total work that's done throughout a process. Okay, so if we're plotting this process path again on a PV diagram, that area underneath is simply the boundary work that's done. So if we know that functional relationship, we solve the integral. Otherwise, we use data points and we calculate it graphically or numerically. So In some cases, we have a functional relationship between pressure and volume that follows this this polytropic relationship where it's P times V to the N is equal to some constant, okay? And so we can rewrite that equation in terms of pressure and put it into our integral. So pressure is equal to C times V to the negative N. This constant varies depending on what type of fluid we're working with and in some cases what type of process. But the basic form of the equation for a polytropic process is just that we have this constant which comes outside the integral V to the negative N dV. And so in this class we looked previously at some special cases where this relationship was known, like for example with an ideal gas or when we're looking at compression processes. So we can see some more specific examples. So if we want to figure out this integral, we can calculate it as such by doing the integration, where this exponent we add 1 to it, and then calculate that integral, divide by the exponent plus 1. So this is the general form of that integration, and it works for every case except for the case where n is equal to 1. That's a special case that I think is on the next slide. So again, we can just take this integration. If we know that we have a polytropic relationship, we can simplify it down into this term here, and that's doing by doing the integration. And again, it only works for integration when n is not equal to 1. When n is equal to 1, then the integral has a logarithmic relationship. So for an ideal gas, PV is equal to MRT. So this looks similar to that equation that we had previously, PV to the minus N is equal to MRT. So in this case, N is just equal to 1, or if we rearrange that. So as we put this into the equation and calculate the boundary work for an ideal gas, then we come up with this relationship here, where the constant is equal to the ideal gas combination of properties. Okay, so as we're defining systems and we start looking at the interactions with the surroundings and taking into account any energy that is crossing the boundary, it's important to use a consistent approach as you do that. And so the approach that's used in this textbook is the intuitive approach, where heat flowing in is a positive quantity and heat flowing out is a negative quantity, meaning it's leaving the system. So ins are positive, outs are negative. So when we look at the total energy change of a system, for a closed system, it's Q in minus Q out plus work in minus work out. So this is the energy in, Q in and work in, and then the energy out is Q out and work out. And by specifically saying that it's Q in and Q out, we've already taken care of the sign for those quantities. So they're always positive quantities when you insert them into the equation, but this little negative sign here will make it so that it's an energy term leaving the system in the form of Q out. So you wouldn't put a negative Q out into that equation. It's already taken, the sign's already taken care of. Yes? No. I mean, we have the ones from last semester in Thermo 1, which if you want that as sheet, I can give it to you. But it's a good idea to take notes so that you can write down a little information about the equation as it's presented so you understand how to use it. Oh, they didn't print out? Like in the PDF? Probably this one, right? Yeah, because it's animated, so you have to write those in. Any that are animated won't show up. Most of them are not animated, but those that are animated don't show up in those prints. So just take good notes. And it's in your textbook too. Okay. So change in energy for a closed system when we're looking at the other side of the equation. So we've talked about heat and work interactions. Now we can look at other energy changes or mechanical energy changes. So it's the sum of these macroscopic and microscopic energies. Macroscopic would be kinetic and potential energy, and then the microscopic or the internal latent energy would be the internal energy of the system. So that's what goes on the opposite side of the equation. So we have Q in minus Q out, work in minus work out, and then all of these other terms are on the other side of the equation. So this represents the change in energy of the system. And in the case where we have a closed system that is stationary, meaning the system itself is not moving, so there's no velocity associated with it, there's no elevation change associated with it, then the kinetic and potential energy terms go to zero, and we're simply left with just the internal energy term on that right side of the equation. So we can write that out fully. Q in minus Q out plus work in minus work out is equal to this 1/2 mv2 squared minus v1 squared, so that's the initial and final state, plus mg h2 minus h1, and this is not enthalpy, it's height. Sometimes we use v, sometimes we use h, and then m times u2 minus u1. So this is the closed system energy balance that would be valid for any closed system. Once you start looking at your particular system, then you can start canceling out terms. So if you don't have any heat transfer, what would a system be called that has no heat transfer? Adiabatic. Okay, so if the problem statement says it's adiabatic, then you know that there's no heat transfer terms. Or if there isn't any boundary work and there's no shaft or electrical work or any other work interactions in your system, then you might cancel out these terms. Or as you begin looking at the system, you might say, okay, I have a work out term, but not work in. Or I have a Q in term, but not Q out. So if you start with this base form of the equation and then cancel things from there, you're more likely to not miss one of the energy terms in your system. But if you jump right into it and just say, okay, Q in is equal to U2 minus U1, you know, you may have neglected boundary work or lost some of the energy interactions as you just jump right into it. I know it's more work to write this down every time, but it will help you organize your thoughts as you solve the problems. So for a closed system that undergoes a cycle, the initial and the final states are identical. So E2 minus E1 is equal to 0, which means the change in energy of the system is equal to 0. So if the net work is equal to the net heat transfer, then we can just say that Q net in is equal to work net out, or Q net out is equal to work net in, depending on whether or not it's a work producing or a work consuming device. So any cycle that, or any system that's operating on a cycle that returns back to its initial state, the primary considerations are your work and heat interactions. So there may be some changes in internal energy or some changes in kinetic and potential energy throughout the cycle, but if you're returning to the initial state, you don't have to worry about those changes that happen. You just need to know the end result of the heat and work interactions. And because cycles often follow a different path, or should follow a different path from the beginning back to the initial state again, then you will have this area under the curve, which is representative of the total work that's done on a PV diagram. Okay, enthalpy and internal energy. So internal energy, I think we kind of know and understand as engineers. But enthalpy, for those of you that have forgotten since last semester, is a property that's a combination of other properties. So it's a combination of the internal energy of the system, which is just the latent sensible energy that every system has because of the fluid that's in it. So fluid itself has some energy level. Well, there's also energy when that fluid begins moving, or as pieces of the fluid have to move other pieces out of the way as it begins to flow. Then there's some energy associated with that fluid having to move other pieces. So it has an energy state that's represented by the internal energy, and then it also has this additional term, this boundary work term, or in the case of a flowing fluid, a pressure times a volume term, which can be combined together to give you another term called enthalpy. So enthalpy is a combination of that internal energy of the fluid plus the energy required to move it. Okay? And it shows up in a closed system when we have boundary work, because that fluid is expanding and contracting within our system. And it shows up in open systems because our fluid pieces are flowing through the system. Okay, so this flow work is analogous to boundary work in a closed system. So just remembering that this enthalpy change is representative of that latent energy plus the energy of motion. So it's almost like a potential and a kinetic energy on microscopic scale for a fluid. So we can find delta U and delta H many different ways. The best method, or the most accurate method, is to use the tabulated data. So if we look in the property tables in the back of the book for any of the fluids that are commonly used within this textbook, water, refrigerant, ideal gases, there will be U and H values that we can just look up directly. So it's easy, it's accurate, and assuming we have the tables available, you can do it quite readily. The alternate way, one of the alternate ways, is to use the functional relationship of the specific heats. So C sub V as a function of temperature, or C sub P as a function of temperature. And this C sub V U is equal to C sub V as a function of temperature multiplied by a change in temperature, delta U. And delta H is equal to C sub P as a function of temperature multiplied by, again, a change in temperature. So if we know this functional relationship between C sub P or C sub V and temperature, then we can integrate. And actually in the back of your book in table A2-C, it gives you one functional relationship for C sub P, and then you can calculate C sub V based on that. So there's 4 different coefficients in front of T terms, and it goes up to T cubed, and it is kind of a cumbersome equation to calculate over and over and over if you're just trying to calculate a change in internal energy. However, it's convenient if you have a computer simulation to put that equation in, and it just automatically will calculate your change in internal energy for you. Less convenient to do by hand. However, what you can do instead of finding this functional relationship is you can say, okay, I know that C sub P is changing over my temperature interval, so I'm just going to assume an average value. And you can do that 2 ways. One way is you can, I might have this on the next slide. No, it's there. So one way is you can say that C sub P at state 1 plus C sub P at state 2 over 2. So you can average it that way. Or you can find C sub P at some T average. So you can, that's T2 plus T1 over 2. So you either find the average temperature and look up your C sub P or your C sub V value, or you look them up at the initial and final temperature and then average those 2 values together. And depending on which way you do it, you're going to have a slightly different answer, but it'll be close enough. And if you're working over relatively small temperature intervals, the error won't be too great because it's fairly linear over small intervals. Okay, so if we're working with solids and liquids, when we look at the definition of enthalpy again, which is this U plus PV term, if we integrate that or derivate that, dH is equal to du plus VdP plus P dV. Now for solids and liquids, we can actually get rid of this dV term because solids and liquids are incompressible, which means their density doesn't change. And because density is equal to 1 over specific volume, it also means their specific volume isn't going to change. So this dV term goes to 0, which means that we can say that delta H is equal to delta U plus V delta P. Okay, so we can just approximate it as that. And so we can say C average is some average specific heat value, delta T plus V delta P. If we also happen to have a constant pressure process, in addition to having an incompressible substance, then this part of the equation also goes away. So we're just left with delta H is equal to delta U. Okay, so that's when the pressure's not changing, and then if for some reason we have an isothermal process instead, then this part of the equation goes away, and we're just left with delta H is equal to V delta P. So again, this is a change in internal energy or a change in enthalpy, and we're, depending on the process and also the substance, we can sometimes apply or use these equations to solve for our terms. Okay, so specific heat. Let's talk about that for a minute and figure out what exactly it is. Specific heat has to do with the energy required to raise the temperature of something. So the specific heat at constant volume is the energy required to raise the temperature of a unit mass of substance by 1 degree as the volume is maintained constant. And then the specific heat at constant pressure, it's the same thing except for now the pressure is maintained constant. So although the derivation of these two property values is based on a constant volume or a constant pressure process, they can be used for any type of process. And C sub V is used to calculate change in internal energy, and C sub P is used to calculate change in enthalpy. And if you have difficulty remembering which one goes with which, if you look at this is how I always remember, is that a V looks more like a U than a P. And a P looks more like an H, I guess, than any whatever. So sometimes, if you don't remember, you can just look it up. So let's do some examples now. And I'm going to use this crazy notepad system, which I've never used before, so hopefully it works for me. So in this example, we have a closed system. And what type of system is it? Or like what's happening in this problem? Say it louder. Okay, so Q in, there's a heat transfer in, and there's also boundary work. How do you know that there's going to be boundary work? I do love those problems, that's right. Okay, so it's a piston cylinder device, and it contains 2 kilograms of water at 125 kilopascals. The initial volume of the cylinder is 0.01 meters cubed. That's nice, it's not in liters. Heat is added until all the water in the cylinder vaporizes. Okay, so what information do we need to use or find out to determine the initial state and the final state and the other things that they're requiring in this problem? So what do we know about this piston cylinder device initially? Okay, we know a pressure and a volume, a total volume, right? Is total volume an intensive property? Say it. No. Okay, and what is an intensive property? Okay, it's independent of the mass or the extent of the system or the size. So volume is not independent of that. How do we make it independent? Okay, what is specific volume? Yeah, volume per mass unit. Are we given the mass in this problem? Yes, that's a good thing. Okay, so if we want to calculate first our specific volume at state 1, it's going to be equal to the total volume divided by the mass at state 1. So we have 0.01 meter cubed divided by our 2 kilograms. So we find our specific volume is equal to 0.005 meters cubed per kilogram. So now do we have 2 independent intensive properties? Yes. So we have our pressure and our specific volume. What is the state of our fluid at this point? If you have your books, follow along. Okay, it would be a mixture. And how do you know that, Patrick? Okay, so what table are you in? A5. So because this V1 is greater than V sub F at 125 kilopascals, then we know we have a saturated liquid vapor mixture. Okay, so because we have a saturated liquid vapor mixture, what do we then need to calculate? quality. Okay, so the quality is equal to V1 minus V sub F over VFG. And if we look on table A5 at 125 kilopascals, we have our V1, which is 0.005, minus V sub F, which is 0.001048, divided by 1.3750 minus 0.001048. And that's meters cubed per kilogram on both of those. I'm leaving the units off just because it's hard to write with this pen. And so we find our X1 is equal to 0.0356, and it's unitless. So that's X1. Okay, can we solve any parts of our problem yet? Part A, do we know the final temperature? From the table at V sub G at 125 kilopascals. Are you looking on table A5? I didn't, is that right? Okay. Okay, so how do we know the final temperature, or how can we figure out the final temperature? We know state 1 now is a saturated liquid vapor mixture. We've calculated the quality. What about state 2? What does the problem statement tell us? Okay, so heat is added until all the water vaporizes. What does that mean? Okay, so the quality is at state 2 is 1. So X2 is equal to 1. So what would our T2 be? Would be the saturation temperature, right? Because it's a piston cylinder device that's not constrained, our pressure will remain the same during this process. So our saturation temperature at 125 kilopascals is 105.97 degrees Celsius. So that's the answer to part A. Okay.
So the saturation temperatures, those are when at that given pressure it vaporizes?
Yeah. So if it's a boiling process, meaning that water is going from liquid to vapor, it's always a constant pressure, constant temperature process, unless there's something intervening to change the pressure. So when it's free to expand, as in a piston cylinder device, and the pressure is not constrained, then the temperature is fixed as well. So the pressure will remain constant, the temperature will remain constant until it reaches that saturated vapor point, and then the temperature will start increasing again. Yeah. But the pressure will still remain the same forever unless something happens to the piston cylinder device. What's,
yeah, a little bit of pressure.
yeah, if you increase the pressure. I think if you decrease the pressure, it would, yeah, increase pressure, it'll condense. Okay. Okay, so how do we find the final volume now? We know that X is equal to 1. We know the mass. How do we find the final volume? Yes. Yes, let's do that. So the specific volume at state 2 is going to be equal to V sub G, which is that 1.3750 meters cubed per kilogram. So V2, capital V, is going to be equal to the mass times specific volume, V2. So, V2, if we calculate that, is 2.75 meters cubed. So you have to sometimes read into the problem statements because it's saying that everything is vaporized. So you go right up into that point where everything is vaporized, and then you take your values. Okay, so that's given in the problem statement. All right, let's see if I can figure this out. Ha. I love this. Okay, so part C, how much heat was added during the process? How would we approach this part of the problem? It's a closed system. No potential or kinetic energies. Okay. Okay, so what is that called? Energy balance, right? I'm all tangled up here. So Q in minus Q out plus work in minus work out is equal to M times U2 minus U1. Those are lowercase u. And because we have no kinetic energy or potential energy, we're just ignoring those terms. Okay, so do we have Q in, Q out, work in, work out? Yes. What is the work out? Boundary work. Boundary work. And then we have initial and final states. So Q in is equal to M times U2 minus U1 plus the work out, which is also the boundary work, right? How would we rewrite boundary work? Yes, and we can simplify that even further because P1 and P2 are the same, right? Okay, so it's the mass times the pressure times lowercase v2 minus v1, so the specific volume. So Qn is equal to m times u2 minus u1 plus m times p v2 minus v1. Okay, but we can do something special with these terms because u2 plus p v2 mass plus m times, no, that's a minus, hold on, I'll erase it. I love this thing. Okay, minus m times u1 plus p v1. Okay, that's also equal to Qn. And then follow my work, that's mass times H2 minus H1. Because these here can be combined into enthalpy. So Qn is just equal to the mass times H2 minus H1, and if we look up the values for that from the table, using our H2 is the H sub G value, and H1 we have to calculate using our quality. I'll leave that to you to do. We get 4,321.56 kilojoules. Okay.
You have to simplify that far, like, after you go down where you have the m times u2 minus u1 plus the mp v2 v1.
Uh-huh.
Do you say there, or you have to keep going to the h?
You could do it that way. You have to look up U2, U1, V2, V1, and plug all those in. Or you combine it and you just look up H2 and H1. So some of those values you already had, and you can do that as an experiment. You can do it both ways. You should get the exact same answer. Because on the table, if you were to look and add U and PV together, you would get that same answer. Okay, any other questions on this problem? Because PV is the boundary work, or we can say P times M times little v. Yeah. So because I'm using specific volume, I have to also include the mass. And I'm using specific volume because that's how I combine it together with the enthalpy, or into enthalpy with the internal energy. Okay, any other questions? All right, so let's talk about the open systems now, where energy is transferred by heat, work, and now mass flow. So when we have additional terms coming in and out of our system, we have Q in, Q out, work in, work out, and energy from the mass in minus energy from the mass out. And because we have a flowing fluid, and generally we have a mass flow rate associated with it, the energy balance is almost always solved in the rate form when we're dealing with open systems. The exceptions would be if we solve it in the per unit mass form, which we sometimes do. So it's very similar to what we did for the open system or for the closed system, but now we have this additional mass flow term that we have to take into account. So when we're talking about open systems in general, we're talking about steady state devices or steady flow devices. We'll talk about unsteady flow at the end as well. But some of the consequences of that mean that the control volume doesn't change. So if it's a steady state device or steady flow device, we don't have pistons that are increasing in volume. We don't have turbines that are changing volume. So our volume is constant, which means we don't have any boundary work to worry about for steady flow. Also, our mass isn't changing. So this dm/dt term, which we would find in a mass balance, is 0. And our energy is not changing. So that is also 0. That doesn't mean we don't have energy interactions going on through our system. It just means that whatever is coming in is balanced by whatever is leaving. So the energy, total energy of the system is not changing over time. Okay, this is only applicable to steady flow. When we talk about unsteady flow, this term does not go to 0. But for steady flow, it does. So then we can write our energy equation like this. So Q in plus work in plus the sum of the mass flow rate times the enthalpy, kinetic energy, and potential energy terms balances out with the other side of the equation where it's Q dot out, work out, and then the sum of the mass flow rate terms on the other side of the equation. We could also write it with Q and W on this side of the equation, and then the mass flow rates on the opposite side of the equation where now it's out minus in. So for conservation of mass, we kind of put the cart before the horse with this term, but let's talk about conservation of mass. So it's essentially very similar to the energy balance in that the net change of mass within the control volume over some specified time period is going to be equal to the total mass coming in minus the total mass leaving. So in other words, the mass in minus the mass out is equal to the change in the mass of the control volume. So again, for a steady flow system, this side of the equation goes to 0 because whatever's coming in eventually leaves again. But for unsteady flow, that's not necessarily the case. So for example, if we're filling up a bathtub, there's mass coming into the tub but not mass leaving if you've plugged the drain. Or maybe the drain's leaking a little bit, so you're putting lots of water in and a little bit's leaking out, eventually your tub will drain. Or if you've opened the drain completely, then there's also that imbalance there. We can also look at the mass flow rate and the mass change over time as well. So we can look at it in the rate form, or we can look at it just in the basic mass balance form. And this should all be review. I'm going through it quickly, but you should know this stuff. Okay, so in general terms, it's written like this. Whoa. That's if we're doing numerical analysis and we have to figure out how the mass is changing across the control volume. We don't usually do that in this class. So if it's steady flow, then the mass flow rate in is equal to the mass flow rate out. And if you have multiple inlets and outlets, you may need to consider the balance there and add those together. But if it's steady flow and there's just a single stream, then M1 is equal to M2. So whatever's coming in is going out in the same quantity. And if it's incompressible flow, then the volumetric flow rates are also equal. So the volumetric flow rate is equal to the density times the velocity times the cross-sectional area. And if our flow is incompressible, that means that our density at the inlet is going to be the same as the density at the outlet. So we can say that these two volumetric flow rates are also equal. So if it's steady, incompressible flow, single stream, then the velocity times the cross-sectional area of the inlet is equal to the velocity and the cross-sectional area of the outlet. Okay, so flow work, we talked a little bit about this. It's very similar to boundary work in that it's the work required to move this piece of fluid into the control volume and then out again. So when we're talking about flow work, it's the same term, it's PV, and it's accounted for in our energy balance because we've already combined it with internal energy. So U plus PV is equal to, I should do this with the pen, enthalpy. Okay, so when we look at our energy balance for an open system, we've already done this calculation, and instead of having internal energy on the right side of the equation, we have enthalpy. Okay, so this U plus PV term is already taken into account. All right, so there's several different types of steady state or steady flow devices. We have nozzles and diffusers. So nozzles increase the velocity of a fluid, diffusers increase the pressure of a fluid, and usually we don't have any work or heat interactions with those, but our kinetic energy change may be significant. Turbines and compressors. Turbines are work-producing devices, so the idea is to remove some of the energy of the fluid as it passes through the turbine blades and take that and use it to like turn a generator and create electricity. But compressors are used to increase the pressure of a fluid, usually gas, ideally a gas, and they require a work input. So they're similar in operation, but they have entirely different purposes. And so sometimes the heat transfer is negligible, not necessarily. Usually kinetic and potential energies are negligible, and we ignore those too. But we always have to take into account the work interactions because they're work producing and work consuming devices. Throttling valves can be any kind of valve that is restricting the flow. So it causes a significant pressure drop in the fluid without having to input any work. And this is used very often in refrigeration cycles. So you have a compressor and then you have a throttling valve, which allows you to change the pressure of the fluid or decrease the pressure of the fluid. And usually there's no work involved. Sometimes there's also a little pump that brings it to the throttling valve, but usually not. And then heat transfer is often negligible, so are kinetic and potential energies. So this is called an isenthalpic process, meaning that H1 is equal to H2. So when you're analyzing or looking at a throttling valve, the primary consideration or the thing that you, I don't know how to make that erase. Hold on. It's there forever now. So generally what, I'm all messed up. Okay. I don't know about this thing. That if you expand out that enthalpy term, because saying just something's equal to something else, that doesn't give you a lot of usable information. But if you expand out the enthalpy term, then you have this internal energy term and a pressure term. So you can determine how much pressure drop you can achieve for a certain diameter tube or something like that. So that's usually what the type of analysis that you would do for a throttling valve is determining the pressure drop and how it affects your final state. Mixing chambers are where two or more fluids are mixed together. So this is different from a heat exchanger because the fluid streams actually come into contact with one another. And usually it's the same type of fluid, so a good example of that is in the shower. You have hot water coming in one side, cold water coming in the other side, and then hopefully a reasonable showering temperature comes out of the spigot. And usually there's no work interactions. Often we neglect any heat transfer or potential or kinetic energies. But what's really interesting is balancing the mass flow because you have two inlets and one outlet in this case. So you can perform the mass balance to determine what's coming in, what's coming out. And if you know the associated enthalpies of each of those fluid streams, then those are the only terms left in your energy balance. Heat exchangers are different from mixing chambers because it's two distinct fluids and all they're doing is transferring heat from one to another. So this is used to cool down a fluid or sometimes to heat up a fluid. And when you look at the entire heat exchanger as your system, then you usually don't have any heat or work interactions. However, if you look at each fluid individually, then you most certainly will have heat interactions because there will be heat transfer crossing the boundary. That's the purpose of a heat exchanger. Okay, so if you take the fluid of each individual one as the system, then you can calculate the heat transfer. And so when you have a heat exchanger as your problem, which you do in your homework, there's 3 possible systems that you can look at and analyze. So you can look at fluid 1, fluid 2, and the whole thing. So depending on your knowns or unknowns, there's 3 different things to look at. And then pipes is just fluid flowing through a pipe. Sometimes we have heat transfer. Sometimes we have work. Just depends on what the system is as it is given. Okay, so those are all the different types of steady flow engineering devices you might encounter. But the basic procedure for analyzing all of those is the same. Okay, so if you start with the energy balance and you work your way forward, start canceling out the terms you do or you don't have and looking at the terms that you do have, then you can end up with any of those equations that were given on those slides there. So you don't need to memorize how to analyze a turbine or how to analyze a compressor because it's all the same. You start with the energy equation. So let's do an example of that. So what is this thing? What is it? A compressor. Okay, air flowing at 7 meters per second is steadily compressed from 150 kilopascals and 27 degrees Celsius to 900 kilopascals and 247 degrees Celsius in an adiabatic compressor. Determine the power input required if the cross-sectional area of the inlet pipe is 0.1 meters squared. Okay, so we want to find this term, work dot in. We're given the inlet conditions, pressure, temperature, and a velocity. And we're given some of the outlet conditions, pressure and temperature. So we want to find work in based on some of these other properties that were given. So before we even begin this problem, what are some assumptions that we can or should make about it? Adiabatic, so Q is equal to 0. What else? Okay, so what's another way of saying that? What's another way of saying it in words? When your mass flow is the same, what kind of a problem? Did you say closed system? Who said closed system? Mass is conserved? Yes, okay. What's another way of saying that? Steady flow. Okay, so m dot in is equal to m dot out. That is the assumption that you make, is that it's steady flow. Okay, and what else? There's one more big one, important one. Has to do with the type of working fluid. Ideal gas. If this was water, could I make the ideal gas assumption? No. Okay, but air is definitely an ideal gas. Okay, so our mass flow rate is given on the turbine or on the compressor. We're given the velocity and we're given some other information about it. I think this is actually not supposed to be there because I calculated the mass flow rate. I copied from another problem, so. Okay. So determine the power input required. What should we do or how should we start? Okay, steady flow energy balance for an open system. So Q dot in minus Q dot out plus work dot in minus work dot out is equal to m dot times H2 minus H1. Okay, I'm given a velocity at the inlet. I'm not given a velocity at the outlet. And that velocity is pretty small, 7 meters per second. It's not very large. So I'm just going to ignore the kinetic and potential energies because they're going to be negligible anyway. Okay, but what do I need this velocity for? Yeah, because that mass flow rate is not correct of the 10 kilograms per second. Okay, so how would I calculate the mass flow rate? Okay. So we need to find our specific volume. And how would we find that? Okay, pressure and temperature, so then we look it up in the table. Okay, we could do that, or, yeah, we could calculate it using the ideal gas law. Okay. Yeah, because it's just based on temperature, right? Yeah, so it's not in that table. It would be in some other tables. If we had more extensive tables, we could look it up, but we don't. So V is equal to RT over P, so V1 is equal to RT1 over P1. And if we look in the back of the book in table A3, we can find our R value for air, which is anybody? Okay, 0.2870 kilopascals times meter cube per kilogram Kelvin. Okay, so we know T and P. We can plug in the numbers to find V, 0.2870. I'm making that worse. Kilopascals times meter cube per kilogram Kelvin, multiplied by the temperature, T1, 27 degrees Celsius. Should I put that in the equation? No, I need to convert it to Kelvin, so it's 300 Kelvin. So multiplied by 300 Kelvin and divided by the pressure, which is 150 kilopascals. So kilopascals cancel out, Kelvin cancels out. I'm left with meters cubed per kilogram, which is what I would want for a specific volume. So I find my specific volume to be equal to 0.574 meters cubed per kilogram. Okay, so how do I use that to find a mass flow rate? What's the relationship between mass flow rate and volume, for example? Okay, there's a velocity term in there. Yes. Okay, so m dot is equal to the velocity times the area divided by the specific volume. We're given the velocity, we're given the area. We don't even have to convert units. So we have 7 meters per second multiplied by 0.1 meters squared divided by our specific volume, which is 0.574 meters cubed per kilogram. So we find m dot is equal to 1.22 kilograms per second. Okay, so we went through all this work to find that term in our energy balance. Okay, so back to our energy balance, what terms can we cancel out? Q in and Q out because it's adiabatic, and work out because it's a compressor. We only have a work in term. Okay, so we have work in is equal to m dot times H2 minus H1. Okay. So we're solving for W dot in, or the power input required. So W dot in is equal to m dot times H2 minus H1. And how do we find H2 and H1? Yeah, so we can use C sub P delta T. So m dot times C sub P T2 minus T1. So if we want to find this average C sub P, what are the two different ways to do it? Yeah, so you can either average the two values or find it at the average temperature. I averaged the two values. So I have a C sub P of 1.004 kilojoules per kilogram Kelvin multiplied by T2, which is 247 Celsius. We can either use Celsius because we're finding a delta T, or we can convert that one also to Kelvin, which I did. So we have 520 Kelvin minus 300 Kelvin. And then multiply it by our mass flow rate, which is 1.22 kilograms per second. So W dot in, if we do the math on that, is equal to 269.47 kilowatts. Okay, any questions on this example? All right, should be very familiar to you by now. Okay, unsteady flow gets a little bit more complicated because now the properties of the control volume do change with time. So mass can be accumulated or drained, energy can be accumulated or drained, the properties are changing. Okay, so usually we study it over a finite time period. We say, okay, initially it's this, at the final state it's this, we have some interval over which we're studying. Steady flow devices, you can say, okay, this is steady state operating conditions. What are the properties at the inlet or the outlet under steady state? Okay, and it doesn't matter the time period so long as it's operating under steady state. But with unsteady flow, you need to know the beginning and the end point because that will make a huge difference in the property values of your system. So again, also with unsteady flow, we can add complications to it, like the boundaries can move or change. And so the size or the shape of the control volume is not necessarily fixed, and the properties are changing. So it gets a little more complicated. But we still start with our general form of the energy equation. Okay, so if we add in some terms, we have a Q in, a work in, and then the mass flow times the flow energy plus kinetic and potential energy. So this is all of our inlet terms. These are our outlet terms, is equal to the mass at the final state times the energy of the final state minus the mass of the initial state minus the energy of the initial state. Okay, so this is the base equation for an unsteady uniform flow. If the flow is not uniform, it becomes exceedingly more complicated. Okay, and in most cases you have to use numerical simulations to figure it out because your time period's changing and the properties are changing across the control volume. And if we neglect kinetic and potential energies, then we have Q in minus Q out plus work in minus work out is equal to the sum of the mass times the enthalpies of every outlet minus the sum of the mass times the enthalpies of whatever's coming in plus M2U2 minus M1U1. Okay, so we need to distinguish between what's coming in and what's coming out and the initial and final states. Okay, because in our previous steady flow problem, maybe we were using M1 as an inlet and M2 as an outlet. In this case, the subscripts 1 and 2 denote initial and final. So as you're writing property terms and you're solving these types of problems, you need to be very careful that you keep your subscripts straight, your ins and your outs versus your initials and your finals. So using I as a subscript is often very confusing because it could be initial or it could be in. I don't like to use I. I like just in. Okay, so the mass balance is similar, that the mass in minus the mass out is equal to the change in the mass of the system, or mass in minus mass out is M final minus M initial. And for control volumes, if the flow is in and out, then you just have an inlet and an exit is equal to M2 minus M1. So again, make sure that you understand your subscripts because there's many different ways to write it. And let's do an example. Okay, so this is an unsteady flow example with a piston-cylinder device. So immediately looking at this, what do you think about that system? What might we need to consider? What do you think? If it's a piston cylinder device, what are some of the things we know about it? Okay, we're going to have a boundary work term. What else? The pressure's constant because it's not constrained in any way, right? There's no piston stops, there's no spring. It's not constrained, so the pressure will be the same from the initial to the final, which is good. It makes the problem easier to solve. What else? What about the working fluid? Yeah, carbon dioxide is an ideal gas, so we can make that assumption. It's an ideal gas. This is an unsteady flow problem. It's also isobaric, meaning the pressure is constant. Okay, what else? No heat transfer, so neglecting any heat transfer, we can also say it's adiabatic. Okay, so, it seems like such a complicated problem, but we just start with what we know and use the energy balance and the mass balance, and we can work our way through it. Okay, so we're going to assume it's also a quasi-equilibrium process. That's how we can say it's isobaric, that this CO2 doesn't flood in so quickly that it throws off the pressure equilibrium inside the cylinder. We're going to assume it keeps pressure. Okay, and the only reason it's flowing is because this is a higher pressure than this. All right, so it's connected to a supply line which has a pressure and a temperature that are slightly different than the interior of this piston cylinder device. So because this is flowing into the piston cylinder device and the pressure is remaining constant, what do you think is going to happen to the temperature? So there's something that's warmer coming in. Do you think the final temperature is going to be higher or lower? Okay, should be higher, right? And it should be somewhere in between 200 and 250 is what we would expect. Oh, actually, they tell us until it reaches 225. All right, so let's start outlining and defining some of our states. So we have state 1, which is our initial state. State 2, which is our final state. And then we're also going to have properties of the inlet. Okay, in this problem, we don't have an outlet, so we don't have to worry about it. We just need to worry about the inlet and the initial and the final state. So what do we know about state 1, or the initial state? Say, yeah, so 125 kilopascal, 200 degrees Celsius. Say that again. Yeah, this is 5 kilograms. Okay, so we know the mass is 5 kilograms initially. What? Oh, okay, yes. Okay, so we know the pressure, we know the temperature, we know the mass of the initial state. What do we know about state 2? Okay, we know the temperature is 225 degrees Celsius. What else do we know? Yeah, the pressure doesn't change, right? So it's also 125 kilopascals. So we can say that. And then what do we know about the inlet? Okay, so it's 500 kilopascals and 250 degrees Celsius. Okay, so that's pretty good. We know the pressure and temperature of all of the states and the inlet, and that's good information to have. Okay, so let's start with our unsteady flow energy balance. We're trying to determine the final volume, and that's it. So we want to find V2. So Q in minus Q out plus work in minus work out plus mass in, H in minus mass out, H out, hard to read, I apologize, is equal to M2U2 minus M1U1. Okay, so let's start canceling out terms. Do we have any heat transfer? No. So Q in and Q out are both 0. What about any work in? No work in. What about work out? Yes, we're going to have boundary work. Do we have mass flowing in? Do we have mass flowing out? No, there's no mass flowing out of our system. And we have a final mass? Yes. Do we have an initial mass? Okay, so our cylinder is not initially empty. There's some mass in it, some is added. So of these terms, what do we already know? We know M1, right? Do we know U1? Yeah, we have enough information to find it because we know the temperature, and we can use C sub V times T. Okay, so we know M1, U1, we know U2. Right now we don't know M2. Do we know how much mass goes in? No, but do we know the enthalpy of what's going in? We could calculate it using C sub P times T. And then, do we know the boundary work? We don't know it because it's dependent on what? V2, right? So this work, we kind of know it. We know V1, but we don't know V2. So this is going to be dependent on the volume. The mass, too, is also going to be somewhat related to the volume. So we're going to end up writing this equation and solving for everything in terms of V2 so that we can solve the whole thing. So it gets a little bit complicated, which means that I'm going to open a separate page because I need to be doing a lot of writing. I think that thing is opening, but I don't know. Yeah, it's going. Do I dare press it again? I don't know about that. There it is. Oh, okay, so open in the background. Okay, so we don't have our proper statement here. Let's see if I can do this so that we can see it. Okay, there we go. Go away. Don't want that. How do I make that go away? No, I don't know. No, okay. All right. We'll do this. Okay. So we have our energy equation. We're just going to rewrite that. Simplifying it, we have negative work out plus the mass in times H in is equal to M2U2 minus M1U1. So that's the simplified form of our energy equation. We can now do a mass balance, which will give us another equation to help solve for some of these unknowns. So mass in minus mass out is equal to M2 minus M1. We don't have any mass leaving the system, so mass in is equal to M2 minus M1. So we can now plug that in up here. We're also going to expand our boundary work term, so we have negative P times V2 minus V1 plus M2 minus M1 multiplied by H in is equal to M2U2 minus M1 U1. Okay, so now we just have two unknowns in our equation, this M2 and this V2. We want to get rid of this M2 unknown as well. It's there twice. So what relationship do we have that relates mass and volume together? Yes, specific volume. The ideal gas law is the one that I was thinking of. Okay, so we can use the ideal gas law. So we know that M2 is going to be equal to P2 V2 over R T2. Okay, and because P1 is equal to P2, we can just call it P. So PV2 over R T2. So if we sub this in to our equation everywhere we have M2 and we collect our terms, we can solve for V2. Are you ready for this? Okay, so V2 multiplied by negative P plus P, oh, and we're substituting in C sub P T in for that, C sub V T2 for that, C sub V T1 for that. Okay, so we're going to collect terms T in over R T2 minus P C sub V over R, that's all multiplied by V2, is equal to negative P2 V1, that's just regular P, plus M1 C sub P T in minus M1 C sub V T1. Okay, so you see how important it is to keep track of your subscripts because we have a couple of different temperatures in here. We have T2, T1, T in, we have M1, and we have the pressure is all the same. Okay, so we solve for V2, we plug in all the numbers here, then we get V2 is equal to 7.52 meters cubed. Okay, so for values for C sub P and C sub V for carbon dioxide, if you look that up in table A3, then you find C sub P is equal to 1.014 kilojoules per kilogram Kelvin, and C sub V is equal to 0.825 kilojoules per kilogram Kelvin, and our R value is 0.1889 kilojoules per kilogram Kelvin. Yes, ideal gas law. Because, all right, here, PV is equal to MRT, or P little v is equal to RT. So I wanted to find an equation that had both V and M in it so I could eliminate one of my unknowns. So I plugged that in for the M so that everything now is in terms of V2, which is my only unknown. Okay. Any other questions on this example? Oh no, now that's not working. My mouse has become my writer and I don't know how to get back. No. Well, that's the last slide anyway. I'll have to figure that out for later. Undo, undo, there. Ah! Okay, so get started on that homework early. Email me if you have any questions. Hopefully these examples give you some help, and I will see you a week from Tuesday. So the following Tuesday, not this Tuesday, but the following Tuesday. Check Blackboard. The lectures will be posted probably by tomorrow afternoon. I've got the first one done. I have to finish the second. So there will be homework, but it won't be super difficult. Yeah. Well, according to my standards. Maybe.